Welcome students. In our today's lecture, we are going to study topic number 1.13, continuous charge distribution. Now, earlier we have studied about discrete charge distribution, and for such charge distribution we have obtained electric force as well as electric field using Coulomb's law and superposition principle. So now that was the discrete charge distribution. Discrete means the charges they are scattered. Suppose Q1, Q2, Q3 and so on. And if any point P is given, and if we want to find the electric field at this point, then the electric field at this point is due to this charge as well as this charge. So individually we obtain the electric field due to all the charges, and then using superposition principle we added that electric field and we get the result. So that was about discrete charge distribution. But in continuous charge distribution you will not find a single charge separately, but in a continuous charge distribution you cannot find such case of scattered charges, because the charges they were distributed over the whole body, and so principle of superposition will not work in this case. So in such type of situation we have to use the concept of charge density. Now these charges which are distributed continuously can be of three types. In three ways these charges can be distributed. They can be distributed in a linear form, they can be distributed on a surface, they can be distributed on some three-dimensional object, that is volume. So now let us see the charges which are distributed on a linear object. So such type of distribution is called linear charge distribution, and so the density related to this is called linear charge density, and the linear charge density is denoted by lambda. Now we have earlier studied about the density, but that density was about mass, and we know that it was denoted by rho. Rho is equal to mass per unit volume. So that was the density of mass, but here the density is of charge. So if the charge is distributed on a linear object, then symbolically we can represent that density as lambda, and according to definition lambda is equal to charge upon length, because linear object has length, and that's why total charge upon total length. Now here you can see this figure in which a linear wire is given, on which the charges they are distributed. You can see this plus sign. These are positive charge which are distributed on this linear wire. Now a small part of the wire is considered here. So as the small part of wire is considered, the charge on that small part is delta Q, and the length of that part is delta L, and this length is called a length element. So here the density of this much part is lambda is equal to delta Q upon delta L is given. Now here the density can be uniform also, or it can be non-uniform also, and that's why the small part is to be taken. So this is about the linear charge density. Now we have this formula. Sometimes in MCQ they may ask about the unit or the dimension of linear charge density. So it is very simple. Unit of linear charge density will be coulomb per meter. Why it is coulomb per meter? Because formula itself says that delta Q in numerator, Q is a charge, so charge is in coulomb, and length is in meter, so coulomb per meter. Now after getting the unit, you can also find the dimension. Next is about the surface charge distribution. Now here you can see this surface. Now for this surface, a small element of the surface is considered. In this small element, the charge distributed are delta Q, and the area of this small element is taken as delta S. So according to definition of surface charge distribution, sigma is equal to delta Q upon delta S, that is the total charge upon total area. The symbol for surface charge density is sigma. So it is clear that as it is a surface, it has area, so total charge upon area. If it was linear object, then linear object has a length, so delta L. And now unit of this surface charge density, total charge upon total area of this small element. Now here it is charge, so charge is in coulomb and area is in meter square. So unit is coulomb per meter square. Now next is volume charge distribution. So here three-dimensional object is considered, and the element, small element of this volume is taken here. The charge on this element is taken as delta Q, and the volume of this small element is taken as delta V. So the volume charge density, symbolically represented by rho, is given by total charge upon total volume. So this is the formula for volume charge density, and now its unit. In numerator it is delta Q, and in denominator it is delta V. So delta Q, which is charge, so it is measured in coulomb, and volume is in meter cube. So unit of volume charge density is coulomb per meter cube. So this is about the continuous charge distribution, and with the help of this concept we can find the electric field or the force around such distribution. Now our next topic is topic number 1.14, Gauss Law. We have used Coulomb's law and superposition principle for discrete charge distribution. But for continuous charge distribution, if we need to find the electric field or the force, then in such case the Gauss law is very helpful, and that's why we have to study about this law. Like other fundamental laws of nature, Gauss law is also one of the fundamental laws. Now to understand this law, let us consider a point charge Q. You can see in this circle. This is a point charge which is enclosed in a sphere. Now here this small charge Q is enclosed in a sphere, and we have considered a small area element of this sphere. You can see this small area element of the sphere. Now from this surface, the electric field due to this charge will be directed towards outside. So you can see the direction of electric field from this small surface is given. Also, we know that for a curved surface, the area vector is also on the same line coming outside. So here you can see that from this surface, the electric field and the area both are in same direction, and we have studied that from any surface area like this, if the electric field passes through such surface, then a flux is linked with it, and that was given by flux phi is equal to E delta S, and it is a dot product because these two are vectors. Now for a flat surface like this, for this type of surface, the area vector is normal to the surface. But if the surface is curved like this, then area vector at any point will be coming out of such surface. And if the surface is like this, that is concave, then at this point the area vector will be towards that point. But here we know that this surface of a sphere is convex, so area vector will be coming out of that surface. So here there is surface also, and there is electric field also. So definitely a flux is linked with this small element, and this flux is very small, so it is taken as delta phi, and that delta phi is equal to E dot delta S. This formula we have studied earlier. This delta S is nothing but it is the area element of this small surface, and so the flux is related to that is also delta phi. Now if we remove this dot, then we know that we have to put a cos theta. So here also it is E delta S cos theta. But as I said earlier that both this area vector as well as electric field, they are in same direction, and so the angle made by these two vectors is 0, as this electric field and delta S they are parallel to each other, angle will be 0. And if the angle is 0, then cos 0 is equal to 1, and so remained is E delta S. So here we obtained flux linked with that small area is E delta S. So this was the flux linked with this small area element, but now we need to find the flux linked with the entire spherical surface, because the electric field is in all the direction due to this charge and the surface is also there. So this electric field is linked with the entire surface. So now the total flux linked with the entire spherical surface is given by phi. Earlier it was delta phi because that was linked with the small area element delta S. Now the total flux is symbolically represented by phi, and phi is given by E into sigma delta S. Here this sigma means summation. Summation of what? The summation of all such small area elements. So if we'll add these all small areas of this sphere, then we will get the total area of the sphere, and so the total flux linked is E into S. Now what is S? So it is summation of delta S, and that is nothing but it is total surface area of the sphere. And so now the entire surface is considered and we get the total flux. So we will give this equation as number 1. Now we know that the electric field due to a single charge is given by E is equal to K Q by R square. So here also I have written this electric field due to charge Q. The value of K is 1 upon 4 pi epsilon naught. Q is here and R square is here. So this is nothing but the formula of electric field due to a single charge. And area of the surface, we know that the area of a sphere is 4 pi r square. So now using this value of E and value of S in equation number 1, we get phi is equal to E and S. See, we have kept these formulas, and now simplifying we get total flux linked with the spherical surface as phi is equal to Q upon epsilon naught. You can see here 4 pi r square in numerator and 4 pi r square in denominator, they will cancel out, and so remained is Q upon epsilon naught. Now some important points regarding Gauss law. Now here this first point says that the Gauss law is true for any closed surface, no matter what its shape or size. So to obtain the formula for the Gauss law, we have considered the spherical surface, but here it is given that the surface can be of any shape, but it must be a closed surface, no matter about the shape or size of the surface. Now, second point, it says that in this formula phi is equal to Q upon epsilon naught. This Q is a total charge which is enclosed by the surface. Means if we consider this surface, and if there are charge particle q1, q2, suppose a charge particle q3 is outside. So here in this formula, this charge is a total charge which is only enclosed by the surface and not which is outside. So this q is nothing but q1 plus q2 in this case. Also, the charge which are enclosed can be anywhere. The location is not important. It must be inside the surface. Now, third point in this equation, phi is equal to E dot delta S. Here there is a printing mistake, so put delta S here. So E dot delta S in vector form. In this equation, the electric field is due to all the charges, either they are inside the surface or outside. No matter about the position of the charge, the electric field is due to all the charges. But as we have studied earlier, the total charge is always which are enclosed and the not which are outside the surface. Now fourth point says that the surface that we choose for the application of Gauss law is called the Gaussian surface. Now suppose if we take a charge q and if we select a closed surface, suppose this is a closed surface like a cube. So this type of closed surface can be considered as a Gaussian surface. It can be of any shape, not that it should be a spherical. It can be of any shape, and such type of surface selected is called a Gaussian surface. Point number 5, Gauss law is useful towards a much easier calculation of electric field when system has some symmetry. Means if the charge distribution on any surface is uniform, then the Gauss law can be used effectively and easily.